When an electric discharge is passed through gaseous hydrogen, then that H2 molecule will dissociate and will produce the energetically excited hydrogen atoms, and which emits the electromagnetic radiation of discrete frequencies. Balmer, on his experimental observation, draw the following equation. This is the wave number. This wave number is equal to 109677. This is the whole number. First bracket 1 by 2 square minus 1 by n square, first bracket close, Cm inverse. And where the n is an integer equal to or greater than the 3, that means n is equal to 3, 4, 5 and so on. And this series of lines is called the Balmer series. Balmer series only restricted by the visible region of the electromagnetic radiation for hydrogen spectrum. Another scientist, Rydberg, noted that all series of lines not restricted with the visible regions in the hydrogen spectrum could be described by the equation. You can see here, it is like Balmer's series of equations, but only 1 by n1 square minus 1 by n2 square, this part he changed. Here the n1, that means n subscript 1, is equal to 1, 2 and so on. And for the n2, n subscript 2 is equal to n1 plus 1, comma, n1 plus 2 and so on. So this is the general equation which Rydberg has discovered. It is applicable for the all regions. We'll see the next slide how it happens. So this is the value in this equation, this constant value 109677. This value is called the Rydberg constant for hydrogen. We have to always put this for hydrogen. Rydberg constant. So what is the Rydberg constant for hydrogen? Its value is the 109677 cm inverse. Now, on the basis of these equations, the first 5 series of lines corresponds to where the n1 is equal to 1, 2, 3, 4, 5. So 5 different wave numbers for the hydrogen, and this is known as Lyman's when the n1 is equal to 1, and when the Balmer series already described when the n1 is equal to 2, and when the Paschen series when the n is equal to 3, for the bracket series when n is equal to 4, and for the Pfund series when the n1 is equal to 5. So here it is clearly mentioned, it is the n1 and it is the n2. So Lyman obviously in the ultraviolet region, Balmer in visible region, Paschen in infrared region, bracket is in infrared region, and Pfund series also in the infrared region. So if you check the following figures, then you can see all the lines, Lyman's, Balmer's, Paschen series, transition of the hydrogen atoms. In this case, if you see, as you know that 3 series, that means when n is equal to 4, n is equal to 5, n is equal to 6. And even the n is equal to infinity, these will be restricted, this line, in the infrared region. And when it is the Balmer series, it is in the visible region, then it will come in this region. And you can see that here different color we have two. But the Lyman series is in an ultraviolet region when the n is equal to 1. That means in equation n1 is equal to 1. Then it is this region. This is the ultraviolet region. And when the n1 in the equation, here it is written n is equal to 2. So when the n1 is a 2, then it is the visible region. And when the number is increasing, then it will go to the infrared region. So with this figure, you have seen the line spectrum of different region.